I want to open with a claim that sounds completely insane, and I want you to tell me whether you believe it. Here it is. If you knew right now exactly where everything in the universe is and exactly how fast each thing is moving, then in principle you could compute every tomorrow that will ever happen and rewind every yesterday that ever did. Nothing left over, nothing up for grabs. The whole of history, past and future, sitting there implied by this lone, frozen instant.
I believe a very carefully worded version of that, yes. And the careful wording turns out to be the entire story of this episode, maybe of the whole series. Because most people either dismiss that claim as science fiction nonsense, or they swallow it whole and draw wild conclusions from it. The truth is more interesting than either, and it hangs on exactly which words you're allowed to keep.
See, that's the part that gets me. My gut says the world is fundamentally messy. Things break, people change their minds, dice land how they land, the weather does whatever it wants. You're telling me all of that is, what, already written down somewhere in advance?
I'm telling you, that's the bet classical mechanics puts on the table. Not the mild, comfortable claim that the world tends to be orderly. Something far more aggressive than that. That underneath the visible mess, there's a machine, and the machine has no freedom in it at all. Give it the setup, and the entire film, running forward and running backward, is completely fixed. There's no wiggle room hidden anywhere for the universe to change its mind.
And that bet actually paid off? Because that's a wild thing to gamble a whole science on.
For a very long time, through the whole rise of modern physics, it kept paying, and it paid spectacularly. Planets, tides, comets, cannonballs, moons, the slow wobble of a spinning top, the swing of a pendulum in a clock tower. The same small handful of rules nailed every bit of it, and nailed it to absurd precision. People predicted where a planet would be far in the future, and it showed up right on schedule. That track record is exactly why we take the bet seriously enough to build a whole course around it.
When you say in principle, though, that little phrase is doing an enormous amount of quiet work in the sentence.
In principle carries almost the whole claim, so let me be plain about it. If the rules are what we think they are, and if you truly possessed perfect information about the setup, then the future is fixed. Whether any real creature could ever get that perfect information is a completely separate question, and a huge part of today is marking where that dream holds up and where it collapses.
Okay, so this is the famous Clockwork Universe. You wind it up, you let it tick, and everything after that is just the gears turning.
You wind it up, you let it tick. And this whole series is really the machinery behind that image. Today we build the 3 rules that wind the clock, and, just as important, we figure out exactly what you'd have to know, what you'd have to hand it, to start the thing running at all. Those 2 projects, the rules and the starting data, are the spine of everything.
3 rules. These are Newton's, I'm assuming, the ones half of us half remember from school.
Newton's 3 laws. Exactly those. And here's my promise for the rest of the episode. The thread I want you pulling on the whole way through. By the end, you're going to see that the most misunderstood word in all of physics is a word you have used your entire life and were completely certain you understood. You use it constantly, without a flicker of doubt.
Which word? Don't leave that dangling, that's cruel.
The word force. Almost everything ordinary intuition believes about force is not just incomplete, it's backwards, pointing the wrong direction. So over the next stretch, we're going to take that word apart, find out why the everyday picture is upside down, and rebuild the thing from the ground up. And after it's rebuilt, the clockwork claim stops sounding insane and starts sounding almost inevitable.
I love that we're barely started, and I'm already finding out I don't understand a word I use constantly and never question. All right, where do we begin breaking things?
We begin with the most reasonable wrong idea any human being has ever had about motion. And you're going to be the person who says it out loud for us because, and I mean this warmly, you already believe it. Everyone does. It takes real work to stop believing it.
Oh, good. I'm the specimen on the table now. Fine. Hand me the wrong idea and I'll say it with feeling.
Let's start with the first of the three laws. Here's the intuition. Picture shoving a book across a table. You give it a push, it slides a little way, and then, what happens to it?
It slows down and it stops. Obviously, that's just what books do when you stop pushing them. I don't even have to run the experiment. I can see it.
Right, and so the natural conclusion, the picture basically every human culture on Earth arrived at independently, is that motion needs a cause. To keep something moving, you have to keep pushing it. The moment you stop pushing, it stops. Push gives you motion. Take away the push, and the motion drains away. Cause on, motion on. Cause off, motion off.
And that matches everything I see. I stop pedaling, the bike coasts a bit and dies. I stop rowing, the boat drifts and quits. I stop dragging the couch stops instantly. It really looks like motion is a thing you have to constantly feed, like a fire that goes out if you stop adding wood.
It looks precisely like that. This is the picture Aristotle wrote down and reasoned about carefully. It's not a stupid idea. It's what the evidence in an ordinary room seems to shout at you. Motion runs out, like fuel in a tank, unless you keep topping it up. If you'd never left an ordinary friction-filled room, you would believe it too, and you'd be reasonable too.
So, where's the trick? You said this whole picture is backwards, which means there's a sleight of hand in it somewhere that I keep missing.
The trick is that there's a second push in the story, and you have simply stopped noticing it because it's always there. When the book slides across the table, it is dragging against that table the whole way. And that contact fights the sliding. It's a push aimed backwards, directly against the motion. We call it friction. So the book doesn't stop because motion ran out of it. It stops because something is actively, continuously pushing it to a stop the entire time it slides.
Friction? Sure, but friction is always there in real life. So functionally, isn't Aristotle still right for practical purposes? In the actual world I live in, things really do stop when I stop pushing them.
In an ordinary room, absolutely, that's what you'll observe. So let's do the thing physics does whenever a hidden influence is muddying the picture. Let's imagine turning that hidden push down, gradually, and watch which way the story bends as we do. Take the same book and set it on smooth ice instead of a wooden table. Now give it the same shove.
It goes way further before it stops, slides across half the rink.
Further. Now polish the ice glacier, colder, smoother. Further still, it barely wants to quit. Now picture a hockey puck on ice so absurdly perfect that there's essentially no drag left at all. You give it a light tap.
And it just keeps going. It doesn't stop.
It keeps going. Straight line, steady speed, and here is the part to sit with. It never needs another tap. Not another touch, ever. The pushing was never the thing keeping it moving. The pushing, back on the table, was only ever there to fight the other push, the friction. Take the friction away, and the motion has no reason to end. It just continues, entirely on its own, with no help from anyone, indefinitely.
Huh. And if I push the idea even further, not ice at all, but a puck floating out in deep space, with nothing touching it, no surface, no air.
Then there is nothing to stop it, and nothing even to slow it, and it glides forever. Same speed, same direction, until the literal end of time, or until something else finally comes along and shoves it. That is the honest, friction-free truth about how motion behaves when you strip the clutter away. And notice, it is the exact opposite of what the ordinary room was shouting at us. The room lied by hiding a push.
Let me test myself on this before we go further. A real puck on real ice does eventually stop, so in the real world there has to be some tiny push slowing it. And if I could somehow delete that push, it would glide forever. The stopping is evidence of a force, not evidence that force is needed to keep it going.
That is exactly the reversal, and you said it cleanly. The stopping is never the motion quietly expiring. It is always some push you can walk up to and point at. Friction with the ice, air dragging on it, something scraping somewhere. Find every such push and delete it, and the gliding has no reason on earth to end. That is the whole content of the first law, boiled down. No push, no change. None.
Okay, say the inversion out loud for me, all the way, cleanly, because I want to be sure I've actually caught the thing and not just nodded along.
The inversion is this. Motion does not need a cause. A change in motion needs a cause. Left completely alone, with no pushes on it at all, a thing does not slow down, does not speed up, and does not turn. It keeps doing what it was already doing. So force is not the thing that makes motion. Force is the thing that makes motion change. We've just moved the word force clear across the story to the far side.
So a puck coasting through space needs no force at all. But then, wait, hold on. A book sitting perfectly still on a shelf, doing absolutely nothing, also needs no force.
Now you're standing right at the strange heart of the first law. Look hard at that book on the shelf. It isn't free of pushes at all. Gravity is pulling it straight down. The shelf is pushing straight up on it, and those two exactly cancel. So the net push, every push added together, comes out to nothing.
Net meaning the leftover, once the downward pull and the upward push have cancelled each other out.
The leftover. And that leftover, no net push, is the very same thing the deep space puck has. The puck with nothing touching it at all. So to nature, the still book and the gliding puck are one situation, not two. Rest is just steady gliding, where the speed happens to be nothing.
That is disorienting. You're saying standing stock still and cruising down the highway at speed are the same state of affairs. Those feel like the two most different things in the world.
The same state, as far as the laws can tell. There's a famous old image for this. Being below decks on a great ship sailing perfectly smoothly, no windows, no way to see out. Galileo's point was that there is no experiment you can perform in that sealed cabin to tell whether the ship is tied up motionless at the dock or racing across dead calm water at a fixed, steady clip. Pour a drink, it pours normally. Toss a ball straight up, it lands right back in your hand, not behind you.
Okay, the ship actually cracks it open for me. If there is no experiment I can do from the inside to tell the difference, then there is no real physical difference to tell. The difference was never in the object. It was in me, comparing it to the shore.
That's inertia. The tendency of a thing to keep on with whatever motion it already has, including no motion at all, right up until a force comes along and changes it. A kind of stubborn loyalty to the present state of motion, which reframes the whole question you started with.
Please, lay it out plainly so I can carry it.
The question, what keeps this thing moving, is simply the wrong question. It has no answer because it has a false premise. Nothing keeps it moving. Moving is its default. The only right question always is, what is changing this motion and by how much? That flip, from hunting for the cause of the motion to hunting for the cause of the change in motion, is the doorway into everything we do for the rest of today and the rest of the series.
Got it. And I'll say it back so it sticks. The default is, keep doing exactly what you're doing. You need a reason to change your motion. You never need a reason to continue it.
Right. Now I have to complicate that a little, because I told you a small fib a moment ago. I said the first law is simply, flatly true. It isn't. It's not true for everybody who might be watching the puck.
Wait, what do you mean it's not true for everybody? It's a law. I thought true for everybody was sort of the entire job description of a law.
You'd think so. But here's a wrinkle inside that same first law. Picture it. You're on a city bus, standing up, holding a hot coffee, and the driver suddenly slams on the brakes. What does the coffee in the cup do?
It lurches forward, sloshes right out over the front lip of the cup and onto my hand. I have personally lived this, more times than I'd like.
It lurches forward.
Now, from your point of view, standing there in the bus, that is bizarre if you take it at face value. Nothing pushed the coffee forward. No hand, no gust of wind. Nothing touched it or tilted the cup. And yet it surged forward all on its own. If the first law were straightforwardly true in your frame, in your bus, that could never, ever happen. A thing with no push on it is not permitted to suddenly accelerate.
But I know why it happened. It's not mysterious. The bus slowed down and the coffee just kept going forward at the speed it already had. Because of inertia, the thing we just talked about, the coffee was loyally doing the default thing while the bus changed underneath it.
And notice the sneaky thing you had to do to solve it. You stepped outside the bus. You explained it from the road. From the solid ground, nothing weird happened at all. The coffee simply kept moving forward at its existing speed, obeying the first law, while the bus braked out from underneath it. The only place in the universe where this looks like a phantom force shoved my coffee is inside the bus, precisely because the bus is the thing changing its motion.
So the coffee is completely innocent. It's the bus that's lying about what's going on.
The bus is the liar. And that gives us a clean way to sort every observer into the honest ones and the lying ones. An honest vantage point, the proper name is an inertial frame, is one where the first law actually holds. A place from which a thing with no push on it really is seen to glide straight and steady. The ground is very close to being such a place. The braking bus flatly is not.
So an inertial frame is basically a place to watch from where you don't have to invent imaginary forces to explain what you're seeing. If your explanations come out clean, you're in a good frame.
That's it, the cleanest way to define the whole idea. Here's the fork in the road. When your coffee lurches, you have two choices. You can invent a mysterious force that shoved it, a force with no hand behind it, no contact, no source anywhere. Or you can admit that your own frame, the bus, is the thing accelerating. Physics takes the second option every time. Needing to conjure up pushes that have no source is your signal that you're watching from an accelerating frame, not that the universe grew a new force for your convenience.
Now I have to ask the properly annoying question. Is the solid ground actually an honest frame? Because the Earth is spinning on its axis and swinging around the sun, and the whole solar system is moving. So surely the ground is secretly a bit of a liar too.
It's the right question, and the straight answer for today is close enough. The Earth's surface is not perfectly inertial for exactly the reasons you rattled off. But for everything in this episode, the corrections from all that spinning and orbiting are so tiny that we can treat the solid ground as a perfectly good inertial frame. That's an approximation. Set it aside for today.
For today. You keep saying things like, for today, and it is a very ominous way to leave a thread hanging.
It should sound ominous, because I'm doing it on purpose. Those lurches, the coffee surge and its whole family, the shove you feel in a turning car, the heaviness in a rising elevator. Hold on to all of them. There's a later episode about the forces that seem to materialize inside accelerating frames and turn out not to be real forces at all. We're not opening that box today. Just remember the coffee. It's a clue we'll cash in.
Filed away, sealed, labelled the coffee. Okay, I feel like we've been circling the big law this whole time. We keep saying force changes motion. But how much? By exactly how much? That has got to be law number 2.
That's the second law, and it is the beating heart of this entire subject. If you remember nothing else from today, make it this. Now, here's the strange part. Everyone on Earth can recite this law. Everyone. Say it with me, you know it by heart. Force equals mass times acceleration.
Force equals mass times acceleration. I had that on an actual poster on my bedroom wall as a teenager, next to a periodic table.
Everyone had it on the poster. And almost everyone stops right there at the slogan. People treat it as a definition or chant it like a mantra, and it's neither of those things. It's a machine. So here it is in a few moves, and I'll warn you, the last move quietly rewires how you see the physical world for good.
All right, I'm braced for the rewiring. Take me through the moves, in order.
The first move we've already earned together. A force does not produce motion, it produces a change in motion. And the proper name for change in motion is acceleration. So, speeding up is acceleration. Slowing down is also acceleration, just aimed the other way. And turning, changing your direction, even while your speed stays exactly the same, is acceleration too. Any change whatsoever to how you are moving counts as acceleration. Force couples to that, to the change, never to the motion itself.
Okay, so force partners with acceleration, not with velocity. A push means a change, not just plain movement. That's already a retuning from the poster, which made it sound like force and motion go together.
Right, and hold that distinction close. The second move, the same push, does not hand every object the same change. Picture an empty shopping cart. You give it a good solid shove and it leaps forward, practically jumps. Now fill that identical cart to the brim with bricks and give it the exact same shove, the same effort, the same push from your hands.
It barely budges. It just sort of grudgingly creeps forward, and mostly it resists me. Same shove, way less result.
Same force, far less acceleration. So some property of that loaded cart resists being sped up. It soaks up your push and gives back much less change. That property is its mass. Mass is stubbornness, a measure of how strongly a thing resists having its motion changed. And be careful how you phrase it. The bricks didn't make the cart want to stop. They made it harder to get going, and by the same token, harder to stop once it's moving, and harder to turn. Stubborn in every direction equally.
So mass just is inertia then. It's the exact same thing from the first law, resistance to change in motion, except now it has a size, a measure, a number you could, in principle, attach to it.
Yes, mass is inertia made quantitative. More mass, more stubborn, less acceleration from the very same push. That's why the two trade off inside the equation. For a given force, the acceleration you get is the push shared out against the mass. Small mass, big response. Big mass, small response. The bigger the mass, the more it eats into the push. You divide the push by the mass.
I feel solid on those first two moves, so what's that last move? The big rewire you promised?
Here it is, and I'm going to go deliberately slowly, because the whole thing lives entirely in the words. We just agreed that acceleration is the rate of change of velocity. How fast your velocity is changing, yes?
Yes, acceleration is how fast the velocity is changing. I'm with you.
But now watch this, because velocity is itself a rate of change. Velocity is how fast your position is changing. So follow the chain link by link. Position is simply where you are. Velocity is the rate at which that position changes. And acceleration is the rate at which that rate changes.
Wait, say that last part again, slower. You lost me right at the end there. Say it again.
Acceleration is the change of position. Watch it climb. Position changing gives you velocity. Velocity changing gives you acceleration. So acceleration sits 2 whole levels above position. Not the change of position, that's just velocity, the first level. The change of position, the second level up. In the language of calculus, if you know it, that's the second derivative, the change of the change.
The change of the change. Okay, so when I look at force equals mass times acceleration, what I am really secretly staring at is force equals mass times the change of position. It's a statement buried 2 levels deep.
That's exactly what you're staring at, and that's the whole reason it's a machine and not a slogan. Now watch what the machine does. You tell me the forces on something. Gravity pulling it, a spring tugging it, a rope, a rocket, whatever happens to be pushing on it right now. The equation converts those forces into an acceleration. It hands you the change of position, right here, right now.
Right, forces go in the front, acceleration comes out the back. That part I can hold.
But here's the loop. That acceleration tells you how the velocity is about to change, so you nudge the velocity forward by that bit. And the velocity tells you how the position is about to change, so you nudge the position forward too. Now you're at a fresh position with a fresh velocity, which means fresh forces. So you feed those back into the front of the machine, get the new acceleration, take the next step. And the next, forever, or until you stop caring.
Oh, it's a loop, it's a crank, it's a handle you just keep turning. And each turn steps the whole thing forward a little.
It is a crank you keep turning. And that's the beating engine of classical physics. Position and velocity go in, the forces hand you back the acceleration, you step everything forward by a hair, then you turn the crank again with the new numbers. Do that over and over, and the object traces out its whole path in front of you. Every position it will ever occupy, in order, like beads on a string. And here's the phrase to carry: you grind the equation forward. You take the state right now and grind it forward, step after step, into the whole future.
Hang on though, the universe isn't literally sitting at a desk doing that arithmetic step by step, is it? That's us, calculating. Or are you saying it makes no difference which?
The steps are our bookkeeping. Nature doesn't sit and compute. The real point is that nothing but the forces and the starting data is needed to fix the path. Let me make it concrete. Throw a ball straight up. The only serious force is gravity, pulling steadily down, so the machine turns that into a downward acceleration and grinds, shaving the upward speed down and down until, for one instant, it's nothing and the ball hangs at the top. Then the same pull keeps grinding and the ball gathers downward speed and comes back to your hand. Nobody drew that arc. The crank drew it, out of the forces and the starting data.
Right, nobody had to know the shape of the arc in advance, it just falls out of turning the handle. But wait, you snuck something past me back there. You said turning counts as acceleration even at a constant speed. That still feels wrong. If my speed isn't changing at all, how am I accelerating?
Good catch. It trips everyone. The resolution is that how you're moving includes which direction you're pointed, not just how fast. Picture swinging a ball on a string around your head at a perfectly steady speed. Its direction is changing every instant. It's constantly being bent away from the straight line it wants to fly off along. So its motion is changing every instant, so it's accelerating the whole way around, and that's why the string has to keep pulling on it. Let go, and there's no more force, so no more change, so it flies off in a dead straight line, just like the first law promised.
Okay, that lands. So the second law isn't really telling me a fact about what force is at all. It's handing me a procedure, a recipe for generating the future out of the present.
That's the entire reframe. It's an engine for turning "here is the complete situation right now" into "here is the entire trajectory." Which raises the most important question in the episode, one so obvious people skip right past it.
Which is what? Ask it.
What exactly do you have to feed the machine to start it running? You said the phrase yourself a moment ago, almost by accident. You said, the state right now. So let's take it seriously. What is the smallest complete description of now that you can hand the machine so that it locks in the whole future?
Well, my first instinct is that you just need to know where everything is. Tell the machine all the positions of everything, hand it the map, and let it rip from there.
Good instinct. Let's test it, because it's the natural guess, and it's wrong in an instructive way. I hand you a photograph, a perfect frozen snapshot of a scene. Everything in it is exactly where it is, pin sharp, not the faintest hint of blur. From that photo alone, can you tell me what happens in the very next moment?
Sure, the ball over here is going to… Wait, no, hang on. If it's a totally frozen photo, I can't actually tell whether that ball is flying to the right, flying to the left, or just sitting perfectly still on a shelf. It's frozen. I know exactly where it is. I have absolutely no idea where it's headed, or how fast.
There it is. Why position alone can never start the machine. A snapshot gives you every where and not a single which way, how fast. It's motion with the motion deleted. Now the exact opposite. I'll tell you every velocity in the scene, every object's speed and direction, but I flatly refuse to tell you where any of them are.
Then I know how everything is moving, but not from where, so I still can't draw any real path at all. I'd be sliding the whole picture around freely with nothing to pin it down to, no anchor. I know the arrows, but not where to plant their tails.
So neither piece on its own is ever enough. Position without velocity is a frozen photo. No future in it. Velocity without position is pure motion, with nowhere to hang it. You need them together, married. You need, for every object in the system, both where it is and how it's moving, captured at the very same instant. Only the pair will do.
And the reason you need both, that's not some accident, is it? That's coming straight from the change of the change thing, because the law does its work all the way down at the level of acceleration, not down at position.
Straight from it. Here's why running the law leaves exactly those two holes. Suppose you know how fast something's speed is changing at every moment, and you try to run that backward to recover the speed itself. You can rebuild how the speed climbed or fell, but not where it started. That one starting value is simply gone. A rate of change never contained it. You have to hand it back by hand.
So undoing a rate always leaves one blank, the value you started from.
One blank, every time. And the law fixes the change of the change, 2 layers deep. So you undo 2 layers to climb back up to position, and each undo leaves its own blank. The first blank is the starting velocity. The second is the starting position. 2 layers of change, 2 starting facts. Both, always both, that's the fingerprint of a law that lives 2 levels down, at what calculus calls the second derivative.
That's satisfyingly clean. The depth of the law tells you exactly how much you're required to know before you're allowed to start it. The math and the what you need to know are the same fact.
The same fact, wearing 2 coats. And that pair, the position and the velocity, right now, for every object in the system, has a name we'll lean on for the rest of this series. We call it the state. The state is the complete starting data, everything the machine needs and nothing it doesn't. Hand it the state, hand it the forces, and the machine is locked. Fully determined.
Locked how tightly, though? Be honest with me. Is it pretty confident best guess locked, or is it something stronger than that?
Not a guess, not a probability. Locked completely. Give the machine the exact state now, plus the rules, and there is one and only one future consistent with it. Not a likely future, the actual path. And here's the part that still gives me a slight chill. The crank turns backward just as cleanly as forward. Run it in reverse, and you get one and only one past. The same state that pins down every tomorrow reconstructs every yesterday. A fully specified present secretly contains all of time, both directions.
The backward part is the piece that really messes with my head. Forward, I can sort of swallow, cause, then effect. That feels natural, that's how I experience life. But you're seriously telling me the present also contains the entire past, folded up inside it?
The same machine, run in reverse. If the state now, plus the rules, pins down the next instant, then, by identical logic, it pins down the previous instant just as firmly. The crank has no preferred direction built into its gears. The laws don't know which way time is supposed to flow. So the present isn't only pregnant with every future, it's a complete record of every past.
But hold on, that fights the whole first half. Friction, the coffee, the couch grinding to a halt, those all look like a one-way street. You never see spilled coffee leak back up into the cup.
You don't, and that's the honest tension. The trick is the level you look at. Down at the true underlying pushes between the tiniest pieces of matter, the bookkeeping runs backward perfectly. Nothing is lost. Friction only looks one way because we don't track every tiny piece. The motion isn't erased, just scattered somewhere too fine for us to follow. Why that scattering has a direction at all is a real puzzle, and a story for much later. Set it aside.
Okay, so that right there is the clockwork. The state right now plus the rules equals the whole of time. That's the thesis from the very top of the episode, the thing that sounded insane, except now I can see the gears it's made of.
That's the whole thesis, and now you've seen why. There's a famous version of this idea, a thought experiment about an imaginary superintelligence, Laplace's, that supposedly knows the exact state of every particle in the universe, and from that computes the entire history of everything, past and future, in a single stroke. It's a vivid way to feel the sheer size of the claim, but treat it strictly as a thought experiment about what the laws imply, not as anything any real being could ever build or carry out. A dramatization, not an engineering spec.
Right, and this is exactly where I push back hard, and I'm fairly sure I'm right too. The real world is not like that clockwork. Weather forecasts fall apart embarrassingly fast. You can't call a coin flip to save your life. If everything really is a perfectly locked clock, why is so much of ordinary life so stubbornly unpredictable?
You're right to push. There are two entirely different ways the real world slips out of the clock's grip. Two different escapes, and they are not the same. Let me keep them apart.
Two ways out. Okay, walk me through them. The first, then the other.
The first way is the big, deep break. And here's where the outer wall of the whole course stands. Quantum mechanics. Go down to the scale of individual particles, and nature stops behaving like a deterministic clock. That clean picture, exact future following from exact present, breaks down, and not merely because we're ignorant of the details, but because that seems to be how the world is built at the bottom. It's real, it's profound, and it's flatly not in this course. This series is classical mechanics, start to finish. Inside these walls, the clock runs perfectly. These are the edges of the course. I'm marking them so you know where they are.
That's fair enough. That's clearly a whole other universe of a subject for another time. So what's the second way out? The escape that isn't quantum?
The second way is subtler and more surprising because it happens even inside the perfect clock. No quantum weirdness at all. Determined does not mean predictable. Picture two runs of the same machine that start almost identical. The two states differ by a hair, far too small to see or measure. In some systems, those runs stay snug together forever, perfectly forecastable. But in others, that hair's width difference grows and grows, feeding on itself, until the two futures blow apart and share nothing. The clock never cheats, never adds randomness, but because you can't pin down the start with infinite precision, you lose the future anyway.
Wait, hold on. So it's fully determined and unpredictable at the very same time? Those two words really do not feel like they should be able to both be true about the same system.
They feel like a flat contradiction, and they aren't. That gap is one of the great subjects of the whole field. Determined is about what the laws do with a perfect, infinitely precise starting state. Predictable is about what you, a finite creature, can do when you're only ever handed a slightly fuzzy one. The clock can be flawless, while your grip on the starting instant is just fuzzy enough to ruin every prediction. Now hold on to this phrase, a slightly different start. The very last episode of the series is about nothing but that.
A slightly different start. Okay, that phrase goes straight into the vault, right next to the coffee cup. I'm starting to suspect this whole episode is secretly a list of things you're going to detonate later. Give me the one big shift underneath all of it. The compact version I can walk away holding.
Both of those are real clues, not throwaway lines. And here's the shift. Before today, you almost certainly pictured the future as something pushed into existence, moment by moment, as if the universe has to keep laboring, keep shoving, at every instant, just to make the next instant happen. Drop that picture. The future isn't pushed along by any ongoing effort. It's sitting there right now, folded up inside two things, and only two: the state of the world and the rules. Nothing strains to keep the world going. Tomorrow is already contained in today, the way the end of a long sentence is already contained in its grammar the instant the sentence begins.
That is somehow both beautiful and quietly terrifying at the same time. The future isn't being made as we go. It's being unfolded, like it was already there. Read out rather than written.
Unfolded is exactly the right word for it. Now, we've built the engine of the clock, and we've figured out what to feed it. There is a final law still to go, and it is the law that people are most completely certain they already understand, and the law they most reliably get wrong. The third law.
Oh, this is the equal and opposite law. Every action has an equal and opposite reaction. I had that on the exact same poster. The line directly below force equals mass times acceleration. I can still see the font.
You did, and that poster is about to quietly betray you, because the slogan is memorable and the meaning is slippery. Let me state the law properly first, carefully. Whenever an object pushes on a second object, that second object pushes back on the first, equally hard, in the exact opposite direction, at the very same instant, not a moment later. Every push is really and truly a pair of pushes. There is simply no such thing in all of nature as a lonely, solitary, unanswered force.
Okay, but hold on, wait. If that is really true, then I've got a serious problem here. If every force always comes bundled with an equal and opposite force, then surely they just cancel each other out. Every push is exactly matched by an equal push the other way, so the total always adds up to nothing at all, which means nothing should ever be able to move, anywhere, ever. And yet, obviously, things move all the time, constantly. So something in what you just said has to be broken.
That's the most common mistake anyone makes about the third law, and the entire fix comes down to one thing: where the two forces land. The two forces in the pair act on different bodies. They never act on the same object, and you only get cancellation when two forces push on the same body. That's the whole knot and the whole untying of it.
Oh, okay, say more. Walk me through it slowly, because I can feel that that's the crux, but I haven't fully closed my hand around it yet. Different bodies. Keep going.
Let's make it completely concrete so there's nowhere for the confusion to hide. You're standing on a skateboard, facing a brick wall, and you reach out and push hard on the wall. That is a pair of forces right there. The first, your hands push on the wall. The second, the wall pushes back on you. Now, here's the whole question. Which of those two forces gets to move you?
Only the second force. The wall pushing on me. The force from my hands is landing on the wall, not on me, so it can't do anything to my motion at all.
Right. To work out how you move, you only add up the forces acting on you, on your body. And on your body, there's just the lone push from the wall. It doesn't get cancelled by your push because your push isn't on you at all. It's over there, on the wall's account. So you roll backwards, away from the wall. You pushed the wall in the same instant the wall pushed you, and the wall's push is what moved you.
So the pair doesn't cancel because the two halves are living on two totally different objects' ledgers. My push is booked to the wall's account. The wall's push is booked to my account. They never land on the same account where they could actually subtract from each other and add up to nothing.
That's the ledger exactly. Different accounts. You only sum forces that share a body, that share an account, and the two members of any partner pair are always booked to two different accounts. That's the deep reason the world is allowed to move at all, and once you see it, you start seeing it everywhere. A swimmer shoves a whole wall of water backwards with her arms. The water shoves her forwards, and she glides down the pool. She isn't so much swimming through the water as throwing water behind her and being thrown ahead in exact exchange.
And a rocket, I'm now guessing, is the very same trick, just with no wall and no water anywhere in sight. It's got nothing external to push on at all.
The very same trick, with nothing external to push against but its own fuel. The rocket hurls hot exhaust gas downward, violently hard, and the gas, in the same instant, hurls the rocket upward, equally hard. It doesn't need air to push against, it doesn't need any ground beneath it. It simply brings its own stuff along to throw. And that, right there, is why a rocket works perfectly out in the vacuum of empty space, which used to confuse people absolutely terribly. There's no wall out there to push on. There doesn't need to be. It pushes on what it throws, and it always brought enough to throw.
Then here's my follow-up, because something's still nagging. If the wall pushes on me exactly as hard as I push on it, dead equal, you said, always equal, then why do I go flying backwards across the room while the wall so obviously doesn't move even a hair?
Oh, that's a beautiful question. And the answer is the second law, walking over to shake hands with the third. Equal forces, wildly unequal masses. That same-sized push barely changes the motion of something as stubborn as a wall, really the whole planet it's bolted to, while the identical push easily changes far less stubborn little you. The wall does get pushed, make no mistake. Its acceleration is just so absurdly tiny you'll never notice it in your life. Same force on both, wildly opposite responses, because mass decides how much each side actually budges.
I really love that these are all secretly the same underlying law wearing different costumes. Skateboard, swimmer, rocket, even just walking down the street. It's the same sentence every time.
It's the same sentence every time. And here's the phrase to keep. You cannot touch anything without being touched by it. You cannot push without being pushed back. Every interaction in the universe is a handshake, never a shove that goes unanswered. And that symmetry, the two pushes always exactly equal, exactly opposite, is quietly hiding something enormous underneath it.
All right, I'll bite. What is it hiding under there?
Think carefully about the bookkeeping again. If the push on this first body and the push on that second body are always exactly equal and exactly opposite, at every instant they interact, then whatever motion-related quantity the first body gains, the second body must lose in equal measure. It's forced, it has no choice. So the pair, taken together as a unit, never changes its combined total of that quantity. Something is being conserved, held fixed for all time, precisely because the pushes always come in these balanced, equal and opposite pairs. The symmetry of the pushes guarantees it.
And you are absolutely not going to tell me what that conserved something actually is, are you? I can hear it coming.
I'll tell you its name and nothing more, strictly as a promise for later. It's called momentum, and it gets its own episode a little later in the series. Where it comes from is exactly this, the equal and opposite pairing of forces you just learned to see. But we don't define it today, and we don't compute a thing with it today. Just hold on to the name.
Name only, understood. Though you're building quite a backlog of things to circle back to.
That's part of what a first episode is for. But before we stop, let me wind all three laws together into the single machine they actually are. Not a list of three separate facts, but a connected whole. Three parts that need each other.
Yes, please do the gather. I want to finally hear the three of them as a whole instead of three things.
Start with the first law. It tells you what motion does when you leave it completely alone. It glides, straight, steady, forever. And rest is just gliding with no speed at all. And quietly, down in the fine print, It tells you where you're allowed to stand to watch honestly, from a frame in which a force-free thing really does glide straight, an inertial frame. So the first law sets the stage and hangs the backdrop.
First law, the default behavior of motion, plus the honest place you're allowed to watch it from. Okay, I've got that beam.
Then the second law walks out onto that stage and says, here is precisely, quantitatively, how a force bends that gliding. It takes the forces and converts them into the change of position, the acceleration, and it does this at every instant, continuously. So what you really have is a machine you grind steadily forward, step after step, turning the state right now into the entire trajectory. That is the engine of the whole clock.
Second law, the engine that bends the glide and grinds out the entire path from it. And crucially, it needs the state, position and velocity, both of them together, before it's even able to start turning.
Both. Always both, or it can't start. And finally, the third law tells you something crucial about the forces that engine runs on. They never come alone. Each force is only half of an equal and opposite pair, the two halves always landing on two different bodies. Forces are handshakes, never solitary shoves. And hidden inside that handshake is a quantity the pair never spends, the one we'll come back to a little later in the series.
So, put the whole thing together for me now. All of it, in a breath if you can manage it.
Here it is. A thing left alone just keeps gliding. A force is the one thing that can bend that gliding, and it bends it by setting the change of position, with the mass sharing out the push. So you feed the machine the state right now, every position and every velocity together, and it grinds out one and only one trajectory, unspooling forward into every tomorrow and backward into every yesterday. And every force it runs on arrives in equal, opposite, simultaneous pairs, landing on different bodies. Give the clock its state, and it hands you back the whole of time. That's the wound clock, the audacious bet from the top of the episode, except now you can see every last gear turning.
And it actually holds together, that's the thing. The claim that sounded flatly insane to me at the very start now just sounds like the machinery. Like a description of how the gears mesh. I can't unsee it now.
Which is the point. You can see the gears now instead of taking them on faith. And here's the door into the very next episode, and it walks in disguised as a complaint. The machine works, but grinding it forward by brute force, step after tiny step, crank turn after crank turn, is exhausting. For a huge amount of what you actually want to know about a system, turning the handle that many times is a miserable amount of labor.
I mean, yeah, grinding that crank step after step after step until the end of time does not sound like a fun way to pass the time. Please tell me there's a shortcut hiding somewhere.
There is, and it's a lovely one. It turns out there's a special quantity that doesn't change at all as the motion unfolds. It stays fixed, holding still, while everything else moves and shifts around it. And if you know that fixed quantity, you can read off, almost at a glance, where a thing can and cannot go, without grinding out the whole path step by painful step. Real answers, almost for free, purely from knowing the number that refuses to move.
A quantity that flatly refuses to change, and that quietly tells you where things are allowed and not allowed to go. Okay, you have to tell me, what is it?
Its name is energy, and it hides itself inside a kind of landscape, hills and valleys that a moving thing rolls up and down through. Next episode, we go hunting for it, and I promise you'll never want to grind a crank again if you can possibly avoid it. But that's the door. We walk through it together next time, not tonight.
Then let me try to hold on to today before we close, all of it, so I don't lose it. Force is not the thing that keeps things moving, it's the thing that changes their motion. The second law isn't a slogan, it's a machine that turns the state right now into the whole future and the whole past. And forces always come in pairs, landing on different bodies, which is the exact reason you can push off of anything at all in this world. Wind the clock, and it tells you all of time.
That's the episode, and a clean catch of it. You came in fairly sure you knew what a force was, and I hope you're leaving just a little unsure, in the good, productive way. And keep this in mind, the clean clockwork is the classical story. The quantum edge at the bottom still stands, and so does the touchy business of a slightly different start. The clock is perfect, our grip on it never quite is. Hold on to the coffee and hold on to the slightly different start. Both come back before this series is done.
The coffee and the slightly different start. Consider them both firmly held. This has been the very first turn of the clock. Thanks for winding it with us. We'll see you next time when we go hunting for energy up in the hills and down in the valleys. And until then, do the thing that changes everything. Stop asking what keeps things moving and start asking what's changing the motion.